Latent growth curves are next on our list of examples to work through. So we're going to look at how to work one of these through the different steps, with the reminder that in this particular model we start with the most restrictive and work our way to the least restrictive, whereas in multi-group models we work from least restrictive to most. So we should see improvements as we go through these models versus multi-group models where they tend to decrease in fit. So we're going to first import the data and name the data. So we have a covariance table. So we have to remember to import that table. And in a latent growth model, you have to have the means because it is a means and covariances model, just like multi-group models. So we have to have those with our covariance table. So we're going to name those means, then the table itself. So if I click on it over here, I see that it's labeled time 1 through 4, and then our means have names as well. So it's a named number over here. Okay. So that is something new, and I forgot to put that in the notes. Okay. Not standard deviations. Standard deviations help you go from a correlation to a covariance table. In this particular case, you need means, and it's part of the CFA code. So the first model we're going to run is an intercept-only model. And so there's no slope, and you want this model to be particularly poor, because if it's the best model, you're saying that the average score is the same for all time points and all participants. We're going to set the variance to 0, so you only get the mean. And the residuals exist. You can't set them to 0 or it will break. But they're all forced to be the same for each time point. So you're saying the variance is the same across time points, which may or may not be true due to sporicity. So let's build that first model. So we're going to include an intercept latent that predicts its time points. So we've got I equals, and you can call this intercept if you want or whatever you wanted, is equal to time 1, time 2, time 3, time 4. But remember that if you think about the pictures that we had in the lecture component, we talked about how you have to set them all to 1. So we're actually not going to do this first line, we're going to do the second line. We set each one of those paths to 1, which forces all of that estimation to happen on the means level at the latent variable. Then we're going to turn off that intercept variance by doing I tilde tilde is 0 times I, so that turns off the variance, and then we're going to set up the residual variances. So remember, what we can do to set them equal to each other is multiply them by the same label, and that forces them to be equal. And so it takes an average of all those residuals for you. So let's look at how this is set up here. So I'm here. So here's my intercept, 1 times time 1, 2, 3, 4. I times 0 times I. I is covariate with 0 times I, which means this is no variance. And then I have 4 residuals. And each one's times R. If you left this off, they would estimate each as separate things, which we don't want to do yet. Excuse me. All right, so the function we're going to use is growth, which operates in a similar fashion to CFA or SIM. And so the way it works is you do the model name that we just built, sample covariance equals covariance, sample mean equals the means column that we have, sample observations, sample size. If we have the entire data set, we don't need those means because it'll calculate them for us. So instead we just do growth model, data equals data. So you can do either one, and it just depends on what type of data that you have imported. So let's run that first model. So if I look at a summary, what I'm going to see is very little on the fit statistics end, so it doesn't give you as many as maybe you would like, but my intercepts have been set to 1, so I'm ignoring that. My regression coefficients have been set to 1. I don't have any intercepts, I've forced those to be nothing, but I do have the I-intercept. The I-intercept is the mean. So the mean of the score across time at the moment is 535. All of my residuals are currently 0.64. So what I've done is include those two estimates. The rest of these are blocked off because we haven't included them yet. And so we have an intercept mean and a residual variance at the moment. I can run fit statistics. So I can get parameter estimates too if I wanted to look at them in a different format with the confidence intervals. But really I want to look at fit measures. So from here I pulled all of the fit values, typed them in here. So look at our RIMC, it's 0.55. This is a terrible model. And then our SRMR, which is 0.52. Our CFI is 0. So really bad model fit. And we would actually be hoping for a terrible model fit in the sense that this should be a bad model. We expect change over time. And at the moment, this implies no change. So our second model is still an intercept-only model, but we're now going to allow the variances to be greater than 0, which means that this is a random intercept model. So we're going to allow people to start in different places and model the fact that some people start a little higher, a little lower than others. Okay. If the variance here is very small, that implies that everyone's starting in the same place. So it's okay if this variance is not significant, but it should improve the model to include that variance component. We're going to force our residual variances to still be the same, and there's still no slope. So all we're really doing is taking out where we force the variances to be 0 and allowing them to do whatever they want. So let us run that. So you still see you have all the r's here, and the intercept times 1 still stays the same. So let's run that bad boy. Look at the summary here. So you'll see our intercept value will change just slightly, but down here in the variances, that's what's happened. So within all of these models, as we go, they should improve in fit and the residuals should drop. So our residuals went from 0.64 to 0.16. So this significantly helped the model. And I could show you that in a minute with change in CFI is what we're going to use. But around this 5.35 mean, what's happening is they're varying about 0.5 point, which isn't a huge variance, but depending on the scale, that might be a lot. In this case, it's not very much. Okay. So I included those. The intercept mean didn't change, and it shouldn't significantly change. The variance, it's varying about 0.5 point up and down, but our residuals went down a lot. And that happened because the error, instead of just being error, now went into the intercept variance. And so we moved the error into something we could understand. If I then run fit measures, I can pull out my SRMR is much happier now. My RIMC is still unacceptable, but it's much better than it was. And then our CFI is 0.838, which is a lot up from 0. So what I did was include that in a, where'd it go? In a model fit table that has disappeared. But if we look at this one, it's the same idea. So here for model 2, here's my model 2 fit, sorry. I have improved by 0.838 over that previous model. Remember, anything over 0.1 is significant. So this model is significantly better. Okay. So let me copy this slide real quick and stick it. Whoops. That did not work. Let's try that again. So copy the slide, stick it right here. So later, that model is there. All right, so significantly better. For our third model, we're adding in the slope component, but a random slope. So random slopes wouldn't really necessarily be good for us because that would imply that everyone is changing in different ways, and we would prefer that everyone change in the same way. But we're going to start by estimating a random slope to see if that's better than no slope at all. And then we estimate the real slope should be even better. So random slope to a real slope should be a better model. So to do that, what we do is we set the slope to 0 still, but allow the slope variance to exist. We are going to uncorrelate the slope and intercept. That's going to get added later. So we're leaving the intercepts and its variance. We're constraining the residuals. That's the same. We're adding slope, but turning off a lot of the slope components. So here I've got my intercept lines, my slope, And so you'll see I've multiplied times 0, 1, 2, 3 to create that slope latent. I'm setting the slope mean to 0. I'm setting the covariance between the slope and the intercept to 0. And those residuals are getting estimated at the same each time. So let's look at a summary there. So now you'll see that I have slope, and here under regression coefficients, there's never going to be any numbers here. Those are set. So if you don't go back and look at a picture of these, you can't use SimPaths to make pictures of these. It doesn't like it. So just make sure that your values here are set. The covariance between the intercept and the slope is 0, which is what we set, and you want that. The intercept for slope, which remember, intercept in this sense means mean, is 0, so we're estimating no slope at the moment. The intercept for the intercept, or the average intercept, is 5.26. It dropped just a little bit. The residual variances dropped more, which is always good for us. And there is a bit of variance around a 0 slope. So essentially what you're saying is the slope is flat. But then you're estimating, well, some people might be flat, but there's a variance in that slope if it isn't flat. But right now what we're doing is setting up to show that the slope is not flat by first saying the slope is flat. So that model, our intercept mean dropped just a touch, our intercept variance stayed the same, residual variance dropped, and our slope variance is about 0.03. Okay, that's kind of small. Is that model significantly? I went from 0.838 to 0.902, and so we're actually approaching here a range of good statistics. So 902 is good. SRMR and MC are not great. You'll notice it actually decreased in fit from 2 to 3. Okay, probably due to complexity. Let's look at fit measures, make sure I did that right. So SMR 1.149, so correct. And 0.19. So these are not acceptable yet. But it is a significant change in the positive direction. So we're going to keep going. Our fourth model, we're going to allow the slope and intercept to vary. So we're going to take out that covariance. So we take off this line. We're going to include a real slope. So this is a model that we said in the lecture should be the best, because it's a actual estimation of slope. And so the point of a latent growth model is to show that things are growing or decreasing, and there is a significant slope. So model 4 really should be the best one. Okay. So we're going to take out the line that says that the slope is 0, and continue to constrain those variances. So where am I at? 4 here. So basically I took model 3 and deleted 2 of the lines. Okay, let's run that. We'll see here, we've got covariance. Let me come back to that covariance. Our intercept dropped just a little bit. Our slope is 0.1311, and it's significant. So huzzah, the slope was good. Our variance dropped a little bit. The spread around the intercept increased just a touch to match with this decrease of the overall average. And the variance for the slope dropped. It says it's a significant variance around that 0.11, but that's pretty small. 0.02 is a small amount of change around that slope. And so if we look at these, they shouldn't change just a whole lot. The residual variance is the one that should go down and down and down and down. It's probably going to decrease a lot at the beginning and then slowly peter off because deconstraining that first model tends to help the most. But these are not changing in a big way. It didn't go from 5 to 10 to 8 to 7. And so if you see big, huge changes, something is kind of suspect, unless you have very big slopes. In our particular case, our slopes are not too large, so 0.11. And the variance around the slope is not too much, which implies that there's not a whole lot of an interaction going on between different slopes in different directions. If you have a slope of about 0 and a very large variance, that's when I tell you to investigate to see kind of what's happening with that slope. Why is the variance so large? Why are some people really high and some people really low? Now back to this covariance. So remember we talked about covariance, and it's the trickiest thing to interpret. And so I have some examples of how to interpret this in a couple slides. But think back, if you remember, a negative covariance means high starting points are correlated with low slopes. And so what's happening here, since the slope is positive, as low slopes meaning closer to zero, so as they start higher, their slope is increasing slower. Here with model fit, is that a significant change? And it is. I don't know why I don't have it starred. There we go. So we go from 0.902 to 0.995. This becomes a very good model. Our chi-square is small, our RIMC is below 0.06, our SRMR is below 0.06, CFI is above 0.95. So this model is very, very good because it is made up. And so that implies that this model is probably can't make it too much better, right? The numbers can't get much better. But what we're going to test is a totally unconstrained model to end. So in this last step, what we're going to do is take out that residual, forcing those residuals to be equal, allowing them to vary. And so if residuals vary at those different time points, that implies that there's bigger error at some time points than others, which is a sporicity issue or heteroskedasticity. So you still would like this model to not be significantly better because residuals should be small and roughly equal. So it really shouldn't be that different from the previous model. But this one actually, typing-wise, is the easiest one to program because you take out all that residual stuff and it's just the intercept and the slope lines. Okay. So let me run that, get our summary here. So remember the coefficients are not changing. I still have that approximately same covariance, that didn't really change. Intercept and slope are about the same, but really what's happening is here. And so those variances go from being 0.11, all of them, to 0.10, 0.11, 0.09, 0.13. That doesn't seem like they're too different. So what we would do is run those fit indices and see if this model is significantly better than a previous model. And if you look at the fit indices for the 4, it's going to be kind of difficult to be significantly better. So we're going to let our residuals be free to vary, so we took out those constraints. Our intercept basically nothing changed, but they all were kind of slightly different numbers instead of all 1, 1. And that model is not significantly better, right? It really can't get any better because the CFI topped out in the last one. I could look at AIC and ECVI, and they would probably be lower in Model 5, but I don't know if that's enough to write home about. Because when you have models that are both that good and approximately the same, remember the simpler model is better. And 4 is a simpler model because all those variances are constrained to one number instead of 4 for each time point. So technically 4 is simpler than 5. And 1 is definitely the simplest. So we're actually getting more complex as we go. You'll see the degrees of freedom are decreasing. And so when you have roughly equal models, you go with the lower model one because that's a simpler model. So let's talk about interpretation. A model with random intercepts was good, so they start in different places, just a little bit around that average starting point. The model with the slope is good, which implies that there is a change over time, so growth did happen. A model with the random slope is not significantly better, so 4 is better than 3, implying that we're changing approximately the same across those time points, which is good, so everybody's changing in the same direction in the same way. But we do have a significant covariance, and it's a negative covariance and a positive slope. So people who start high go up slower, people who start lower go up faster, right? And so with that interpretation, you just have to remember that negative covariances are high intercepts are tied to lower slopes, meaning closer to 0 or more negative slopes. But the slopes in this case were positive, so I meant closer to 0. If your slopes are negative, it's the reverse situation. Okay. So altogether, that's a latent growth model. Just remembering that you want model 4 to be the best model, and you're comparing them successively, and each model adds a component, releases a component, so it adds more complexity to allow to estimate for the intercepts, a random intercept, random slopes, a overall slope, and then covariance. And then in 5 is residual variances. So we'd prefer model 4 to be the best because it implies that growth happened, but not in a random way, and our errors are approximately the same for each time point.